Good morning, my geeslings. It's the introduction for episode 31 with Haim Gaifman, who is a philosopher, mathematician, probability theorist, computer science scientist at Columbia University. This is our fourth episode. So he was on episode 1, episode 11, 21, 31. Well, no, 31. And this is the fourth we recorded back when I was still in New York City, maybe 6 or 7 months ago. And they were some of the first episodes that I did. I'm sitting here now. I just ate this pint of pear and blue cheese ice cream, which I was absolutely terrified about eating in because I really don't like blue cheese, but it didn't turn out as terribly as I had expected. And I don't know why I wanted to share that with you. Maybe because I feel proud for how adventurous I am. Yet, as you might know if you've listened to other episodes, I'm very much determined to experience everything the world of ice cream has to offer. But back to the introduction to the episode, which I probably shouldn't have strayed from. Haim and I talk about George Cantor and set theory, Richard's paradox, and infinity. This episode was much drier and more mathematic than any I've done so far. And in that sense, I think it might have been a failure. Not that obviously I find the material very interesting. And even though it was pretty basic as far as actual work on these topics goes, it might be too intense even at the low level at which we speak of it for a general podcast audience. So I'm not sure. Maybe people will let me know they like it and they want even more technical material. I intend to have some episodes like that here and again. But I should also note, Haim would want me to note that I didn't give him any time really to prepare. I just kind of sprung the topic on him at the last moment. So if there are any errors, don't hold him accountable. Put them on Mother Goose. All errors. And then the last thing I should say is I interrupted Haim way too much. I would hope that you don't take that as indicating that I'm a generally rude person. I try not to be. But, Haim and I are very close. He's like an honorary third grandfather for me, so it's not... it's just part and parcel of our conversation. But I also wanted to try to make sure that we were giving enough background and not going too fast. So I felt that I had to stop him to make sure that we went over some basic things and clarified things as we were going. With all that said, I hope you enjoy the episode. And I'm in New York. I'm not in New York. I'm in Palo Alto. He's in New York, but I'm sure we'll do some more virtual episodes going forward because he's really a gold mine on all sorts of topics in philosophy and the other aforementioned fields of which he is a part. Richard's paradox.
Okay, wait a minute. This has to do with the technique which is called diagonalization.
Well, first, I think we should begin with
Canto.
Yes, precisely.
Okay.
So, for somebody who doesn't know who George Cantor is, let's talk about who Cantor was and what set theory is to begin with.
Okay, so that's a talk all by itself. Cantor was a terrific mathematician he started by doing work in Fourier analysis and hardcore subjects, and he had very good results. He came as a young man. He came from Russia, out of a mixed background. He established itself eventually at Halle, which is a decent university in Germany, not the top universities in mathematics, which would be the University of Berlin, or the other famous university, where Hilbert taught, and
Jena?
no, Jena was the University of Frege.
Okay.
Now, what is
Gothenburg?
Yes. Not. Wait a minute. Can you repeat that?
It might be the English version, but Gothenburg. Let's see. I'll look it up. Hilbert, Germany, or I'll just look up Cantor. George Cantor.
No, that will not tell you what. The University of Göttingen.
Yes.
Not
Göttingen.
Gothenburg. The
But it's
University of
Gothenburgen. I think that's how we call it in English. But
no,
maybe I'm totally...
Göttingen. I mean, you cannot transform Göttingen into Gothenburg.
Okay.
I mean, it's not a question of pronunciation. It's really wrong.
Well, let's find out.
Gothenburg has another meaning than
Göttingen.
Göttingen. Okay, there were two great famous universities. The famous university where strong work in mathematics was done. Remember, we are comparing universities who dealt with everything. So some of them were more philosophically oriented, some more humanistically oriented, natural science, and so on. Germany was a very big center of mathematics. So the flagship, so to speak, of Hilbert was the University of Göttingen, and there was also the University of Berlin.
But anyway, going back to Cantor at Göttingen.
Okay, fine. So Cantor did some very decent work in Fourier analysis, which is actually something that brought him to the consideration of point sets in the plane. Okay, so some point sets, so there are countable point sets, and they are...
But first we need to discuss what a set is.
Okay. No, the set, the abstract concept of a set didn't figure at that time.
Okay. So point sets
there was perhaps
predated set theory.
Yes, point sets, collections or something like that. There were sub-regions of the real numbers or of the plane.
Okay.
Okay, so the abstract collection of a concept of a set was introduced by Cantor. Now we can have a whole talk about Cantor, what he did and what he didn't do and so on. But eventually he started to make more and more observations of a general character about the sets themselves rather than the mathematical structure that goes with the set.
But his motivation for, tell me if I'm wrong,
Mm-hmm.
I mean, today people think of sets as, in a sense, the objects about which mathematics is.
No,
I mean, you might disagree with that, but now that's something that some people think. Hold on.
Even Kanto didn't think
Right,
that.
but Cantor didn't think that.
No.
Cantor's motivation was to study infinity.
Yes.
Okay.
So Kanto didn't think so because...
But first, what is a set? What did he think a set was?
Okay, so set is a collection of points. Usually this would be in the plane because this is where it started, or in a three-dimensional space. So it was a subset of a geometrical space. This is how it would be. And Some sets are finite and some sets are infinite. And then he had the idea
But now sets, I mean, so there's the set of you and me. That's a set of two objects.
Yes,
there's the set of the natural numbers. That's an infinite set.
Yes, but you see, this is a much later construction.
Okay, back then sets were just points in the geometrical plane.
Yes.
Okay.
That's all.
I'm just trying to explicate what a set is as we go along. That's all.
Okay, so you are viewing it from the later point of view. He started his research at the end of the 19th century. We are speaking about his first works is 1870 even. Goes back as much as that. And then he went on in 1889, 1890, and that's about it. And he finished his work there at 19-something. Okay? At the beginning of the 20th century. And then there was the First World War, he retired, and that was the end of his war. So most of his work took place before the 20th century. It was the end of the 19th century. And he wanted to abstract from various properties of the set, okay? And one abstraction was usually the sets were ordered. Sets of natural numbers. So the sets came with an ordering. So first of all,
so the set of the natural numbers 1, 2, 3, 4, 5, 6, 7, or is starting with 0 if you want. You're saying it's ordered.
Yes, it is ordered. Okay. So the sets which arrived at mathematics were ordered sets usually.
At the time he began, when people thought of collections.
Right. And so he introduced an abstract notion of the cardinality of a set, and two sets were of the same cardinality if there was a one-to-one function mapping the members of one set onto the members of the other set.
And that already comes from Hume, though, right?
This is when two sets have the same, but Cantor introduces, so to speak, cardinalities as an abstract way to measure sets. And the cardinalities were, if you take a set A, the cardinality of A is A, denoted as A, with two bars over it, two horizontal bars. This was, so to speak, abstraction. The first bar means you disregard all other things except the ordering of the set. And even if you also abstract from the ordering itself, whatever it is, then you get an abstract notion of the cardinality.
Okay.
So
and this was his symbolism?
Yes. This was his symbolism and his idea. Hume's of... I don't know. Cantor was very, very well-read philosophers. I don't know if he refers to Hume's criterion when two sets have the same cardinality, if there is a one-to-one function, and so on. And then he noted that some sets are finite, and then there are countable sets, like the sets of natural numbers that can be arranged in a sequence.
So what does that mean? What does it mean to say that one set is finite?
It's either has no elements or it has one element. No, so we start with either it is a set whose only there is a single element or two elements or three elements and four elements, etc.
So finite is taken already as understood?
Yes.
Okay, and then what does it mean if it's not finite, then what does it mean for it to be countable?
Countable means that it is either finite or it has the same cardinality as the natural numbers. the whole natural numbers, 1, 2, 3. That means you can count them, like you count with natural numbers, in which case it will be infinite, but have the same cardinality as the cardinality of the natural numbers.
Okay.
But it means that you can arrange its members in a sequence, which will be either a finite sequence, or it will be like the sequence of natural numbers. Okay?
Okay.
And then Cantor asked himself, what about sets that have higher cardinalities than the natural numbers?
First, before we go into sets that have higher cardinalities than the natural numbers, can you explain, for instance, why the set of even numbers is countable and of the same cardinality as the set of all natural numbers? Because it's intuitively one would think that the set of natural numbers would be twice as large as the set of even natural numbers.
That is correct. And that is because there is the one-to-one function which maps the set of all natural numbers onto the set of all even numbers.
So what is the function?
The function is n goes to 2n.
Okay. So 1 goes to 2.
And 1 goes to 2, 2 goes to 4, 3 goes to 6, and so on.
And in this way, you see that they're of the same size.
Yes.
And that's an example of how the even numbers are of countable cardinality because the natural numbers are of...
Yes, and of the same cardinality as...
And then for an infinite collection to be uncountable, it means that there is no such bijective function with the natural numbers.
Right. Now, immediately, of course, there is the obvious paradox that this notion allows for a subset to have the same cardinality as a whole set.
So why is that?
Because of the subset of even numbers is a much smaller set intuitively than the set of all natural numbers, but they have the same cardinality.
Okay, and that's a paradox.
This is a paradox.
Does that paradox have a name?
I think it was one of the paradoxes. Galileo already noticed it.
So I'll rephrase it.
It was already known in late and ancient philosophy.
So I'll just rephrase it very quickly. So with all the finite numbers, let's say the finite number 4.
No, for finite sets, this cannot be the case.
Right. So 2 is a subset of 4, but they're not equal.
Yes.
And that is intuitive.
Yes.
But it is not clear at all that the even numbers, which are a subset of the natural numbers, would be the same size as the natural numbers.
Yes.
And that is what results in this paradox.
Yeah, this results.
And you say it's been known since antiquity.
Yes. That has been known as antiquity.
But Cantor showed that it was not a paradox.
No.
He didn't. Okay.
I mean, whether it's a paradox or not depends on your point of view. You see, if you are considering only finite sets, there is no paradox. Now, Cantor wanted also to take the totality of all natural numbers as a set. This would be an infinite set. And the intuitions which are obvious in the case of finite sets are not the same in the case of infinite sets.
Right, because as Abraham Robinson might put, it's very easy for me to conceive of this collection of 4 chairs here, but it's not at all easy for me to conceive of an infinite collection of chairs. And it's sort of my intuitions, which are so obvious about this set of 4 chairs, leads me to project illicitly onto an infinite collection.
Right. So Cantor went boldly and says, yes, this is true for finite sets, but let's have a notion which applies also to infinite sets, like the set of all natural numbers. And let's go on and see. So for finite sets, a proper subset is always of smaller cardinality. This breaks down in the case of infinite sets. Okay.
Right. And now, again, so somebody who is a finitist, somebody who does not believe in infinite collections, they might take this as evidence against the existence of infinite sets. This paradox, they say, this is just not possible, so we must reject infinite sets.
This is already mentioned by Galileo a long time before that, and He said this shows that there is no such thing as infinite sets and so on and so forth.
Well, what's fascinating about this already to me is that it goes back to our earlier discussions of paradox, where you find that the way to resolve paradoxes or to discuss them is almost always you go back to the assumptions that underlie the argument that results in the construction of the paradox.
That is correct. But sometimes this construction, these assumptions are, so to speak, hidden.
Right.
And once you expose them, there is no paradox.
Mm-hmm.
Here, you can boldly say it is a paradoxical because you rely on your usual way of representing sets, which are finite sets. So you have a good notions of finite sets, but this notion becomes radically different if you consider infinite sets. So in infinite sets, certain things which are true for finite sets simply break down. And let us go on and see if we can investigate infinite sets as a subject of study. Okay?
Mm-hmm.
So the first question which Cantor asked himself was, okay, let's take the sets of all the points in the plane, in the two-dimensional plane. And let us take the set of natural numbers. Both of them are infinite. Obviously, the natural numbers can be embedded in the set of all points because you can have a coordinate system and you can have a line and then marks 0, 1, 2, 3, 4 or something like that. So obviously, the cardinality of the set of all points is greater or equal than the cardinality of a countable set. But is it strictly bigger? Can you show that you cannot enumerate all the points in the plane or all the points on a line?
So what this gets back to is we already discussed countably infinite sets.
Yes.
So the natural numbers being of the same cardinality as the even numbers.
Yes.
So the question then is, are there sets that are larger than that?
Yes.
That's the question that he
Yes.
was wondering.
And the obvious candidate would be the set of all points on a line or the set of all points on a plane and so on.
So if we imagine, just for the audience that's listening, the number line that goes 0, 1, 2, 3,
Yes,
4, 5,
yeah.
with all these ticks. And then we imagine all of the ticks between those ticks that could possibly be made.
Okay.
And we wonder...
But you have to... The intuitions there are geometrical. That
Right.
is the point.
But it's still the question is still, are these two collections, the 0, 1, 2, 3, 4, 5
Yeah.
collection, and then the collection with all those ticks, are they also of the same size?
Yes. All those things mean what is in analysis considered as real numbers.
Yes.
Okay.
And there's also the rational numbers, but we're not
Yes.
talking about
No,
those right
rational numbers can be, it's not difficult to see that
Right,
they
they're
are
of the same
countable.
card,
Yes.
but right.
So it was for Cantor, it was an open problem.
Mm-hmm.
So he posed himself this problem.
Which is now known as the continuum problem.
No, this is not the continuum problem. This is a problem where...
Right, okay, you're right. It's not.
Okay. It's not. It's completely different.
Yes,
And-
completely different.
And then he
related.
asked himself, nowadays, of course, it's trivial because the answer is known, are they of the same cardinality? And then Cantor, in the 1870s, had an argument to show it is not the case, but that the cardinality of all the points on the line must be greater than the cardinality of the natural numbers.
Right, and the continuum problem then is
wait
whether
a
or
minute,
not there are any
wait,
cardinalities
yes,
between.
yeah.
I just have to make it clear that I did know what I was talking about a little bit.
Okay, fine.
Is whether there are any cardinalities
Right, yes.
between them.
But the interesting point is that he used for the proof of that certain theorems from from actually probability constructions of probability measures and so
Isn't
on.
is this not where the diagonalization argument
No,
comes
no,
in?
no, no,
Okay.
no. He used very particular arguments from probability theory, the way you define probabilities and measure theory and things like that, that were dependent also on the topology of the real line. You see, there are topological notions of the real line. Here you have to really to be very much aware of the history of mathematics. That the history of mathematics already at that time they knew how to define probabilities and to prove things because they had to compute areas and integration. This was the 19th century, and in the 19th century, there was also a revolution in mathematics itself. Mathematics itself was revolutionized, and in a way that led later to set theory, but it was already revolutionized because there was a calculus of Newton and Leibniz, which was 200 years before that, and they had the calculus. And so mathematical history, you see a mixture of ideas, and this is not the neat, nice constructions that you come and see in retrospect. From once you accomplish the whole thing, you will see a nice way of how to generalize, but usually history doesn't work like that. So the first proofs was a proof which relies very much on what the topological properties and on the fact that you can define a measure, and the measure had certain properties. And put it like this: suppose that the measure of the whole the set of natural numbers on the real line was the same as the whole line itself, okay? Then what you can do is you take the first, you take the first natural number and you cover it with an interval of length, say 1 over, 1 over a quarter. You take an interval 1 over a quarter, then the other 1 over an 8, and then 1 over 1/16, and so on. And so you cover all the set of all natural numbers with a sequence of intervals whose sum, you see 1 over 4 plus 1 over 8, and so on. This is even less than 1/2. And this is impossible by probability theory. So he evoked notions from probability theory to show that this is impossible. Is this clear?
Mm-hmm.
So he gave an answer. No, it is impossible. In 1889, I think I know exactly where he got I was really interested. In 1889, he found a completely new technique which didn't rely on topology and on probability theory and so on, but purely, you might say, it's a set theoretic technique to show that the set of all natural numbers has smaller cardinality than the set of the whole of all real numbers. And but what it actually, I think the beginning was to show that with every set he associated the set of all subsets of the set. Okay, so for instance, if you have an empty set, there is only one subset of the empty set, which is the empty set itself. Mm-hmm. Okay, so the set of all subsets here is 1. If you have a set with 2 members, the set of all proper subsets is 4. Okay, 3, it is 8. So this power set jumps very. It's
2 to the n minus 1.
2 to the n.
2 to the n.
2 to the n. If a set has n members, the set of all subsets is 2 to the n. This is for finite sets. Now for infinite sets, it is also a much bigger set, the set of all subsets. But he found a direct argument to show it. So suppose...
And this is the diagonalization?
This is a diagonalization. Now suppose I'm actually doing here a talk in the history of mathematics, and very, very fast. Because we will, if you really want to do it, you have to do it in detail.
Right, and you can watch videos on YouTube of somebody drawing out and writing out Cantor's diagonalization argument,
yes.
But we'll
it's
talk
possible.
through it.
Look, usually it's very difficult. This video recordings of lectures, usually if all that you have is a video, usually the video would be too fast for you to understand. The lecturer has a natural inclination to, okay, so you do this, and he condensed it. If you really want to learn from videos, you have to record a real class in which students ask natural questions as they come to them. And you should take care that there would be enough natural questions so that if anyone has any doubt, he would be able to find some student who asks natural questions, or that the lecture is being slowed down.
Maybe that's one reason podcasts are successful, because people like me who aren't understanding what's being told to them are asking questions and getting clarification in real time.
Yes, but this should be visual also. So yes, you can teach. Usually, this is an enormous project to teach not to teach in real class, by electronic teaching or teaching. The real candidate for teaching by on the internet or in TV is really to photo a real class of people who ask questions, and also to, so to speak, have some kinds of direction. There should be a director who would be aware of the natural questions and, so to speak, put their students who will ask the natural questions.
But so let's get back to the diagonalization argument, because that's what's going to lead into Richard's paradox.
Okay, so the diagonalization argument is the following. Here it really should be visual, and then you'll see why it's diagonalization.
Mm-hmm.
So suppose you have the first set, which is, let us call it A1. You can start from 0, but let's call it A1.
Okay, so
let us natural numbers be 1, 2, 3, 4. So there is a set A1, and then for every subset can be represented by what is sometimes called an indicator function. The indicator function is a function which gives every member who is in the subset the value 1, and if it is not in the subset, the value 0. If you want to switch them around, you can switch them around. So this is the indicator function. That means every member of the subset gets one of two values, depending whether it is in the set or not in the set.
Okay.
So you take the first set and you put it, say, A1, A2, A3, A4, and so on. And each one of them is actually a set which is a function which has value either 1 or 0, dependent if the member is not or is. Now you can do the following.
So each set is a string of ones and zeros.
Yes.
Okay. So you have A1, A2, A3, A4, and each is just a set of 0, 1, 0, 0, 0, 1.
Yes,
it's just a string of that. Okay.
Now what you do...
How many of those are there? An infinite amount.
There are infinite amount, but there are, suppose per contradictions that you can enumerate all the subsets.
Okay.
Then all the subsets, there will be A1 the first subset, A2 the second, there will be an enumeration.
Sure.
Now what you do is you take the diagonal. That means in A1 you take the first member. In A2 you take the second member. In A3 you take the third member, and you toggle them. If the value is 0, you put it to 1, and if the value is 1, put it to 0.
Mm-hmm.
Okay? This gives you the diagonal,
Uh-huh.
and then you say this diagonal itself also represents a set. But the set is not among the sets that you enumerated, because if you take, suppose it was the k set, then you see that the k number belongs to it only if it doesn't belong to it.
So this diagonal number can't be A1 because the first
changed.
The first position is the opposite,
yes.
and it can't be A2 because the second position is the opposite.
Okay.
So what he's done is constructed an argument that shows that
Yes.
there is. We suppose that we could list every number in this collection,
Right.
and we have just constructed one that isn't in it. So we've generated a contradiction.
That is correct.
And so what does this tell us?
Tell us that the power set has always higher cardinality.
So that the power set of an infinite cardinality
Yes.
always has higher cardinality.
Yes.
Okay.
A power set, in this case, is case of natural numbers.
Right.
But the argument is sufficiently formal, it generalized to any set.
So what it tells us, though, is that the power set, which is the set of the subsets of the natural numbers, which was 0, 1, 2, 3, 4, 5, 6, 7,
right.
is larger than the natural numbers themselves.
Yes, in terms of cardinality.
In terms of cardinality.
But it will work for any set whatsoever.
Okay.
Okay, so the power set of a set is always larger cardinality. This is the diagonal. Cantor noticed that this is, and if you read the original paper, it is so verbose, and let us associate this with this and this with this. You fail to, it's not what I just told you in 3 minutes.
Mm-hmm.
It's a let us do this, and let us have this notation and this notation. But the argument is exactly the argument I gave you, okay?
Mm-hmm.
And then Cantor noted that it doesn't apply only to the natural numbers, but that it is a sufficient abstract argument that can apply to every set.
Every infinite set.
Every finite or infinite set. If you have a finite set, for finite set we know also that exponentiation always is
Right.
high.
Okay.
But the subsets is low. But this argument applies just in general. Okay, so the power set of a set always has larger cardinality than the set. Okay, so this was Cantor's diagonal. So this is diagonalization. Okay, fine. So this is the first stage. This is a technique of diagonalization.
And is this the way that he proved that there must be an infinite set of larger cardinality than the natural numbers?
No, originally he proved by probabilistic methods.
Right, okay. And this was the simpler argument.
This was a simpler argument, but
and one that generalized.
Yes, to any set whatsoever.
Okay. Did the original method generalize?
No, because you don't have probabilities of arbitrary sets and so on.
So this one is much more powerful.
This one is much more...
And much more intuitive.
Yes. And so, well, it's intuitive because you don't know probability, but if...
Yeah, okay.
But for him, it was specific to that. So he did it in 1889 and immediately realized that he has a very powerful tool here, that the whole thing, and that this generalizes, and this is the diagonal method. Okay? So this is Cantor's contribution. Now, therefore, Cantor realized that the powers themselves are not limited in any way. For every set, the cardinality of the set of all subsets, he thought that for every set you have also the set of all subsets of the set.
So when you say the powers are not limited, you mean that this notion of set, it can just keep getting bigger and bigger as long as you keep taking power sets?
Yes.
Okay.
So he said, okay, so...
There must be an infinite number of cardinalities of infinity.
Wait a minute. Let's not
Let's
not rush.
Well,
but,
okay.
But this showed to Cantor that the theory of infinities can be a very complicated theory because it is not either finite or infinite.
Right.
Because the infinities themselves have grades, so to speak. They have higher infinities and smaller infinities. And he saw himself as a researcher who generalizes the notion of a set so as to also capture infinite sets. So he saw himself as one who investigates infinities.
Mm-hmm.
And for him, infinities were legitimate. These are the infinities, and this
unlike a finitist, obviously.
Huh?
Unlike a finitist
Yes,
who rejects it at the outset.
Well, okay. No, but so he saw himself as establishing a theory of infinities. But he didn't saw himself as establishing a theory to which all mathematics can be reduced.
Right, which is a more modern idea that all mathematics can be reduced to set
Yes,
theory.
this is this was realized in 1920 already. There were indications that you can do that.
Mm-hmm.
Okay, there was a lot of contributors. An important contributor was von Neumann.
Right. And this, of course, what Cantor did was called naive set theory. Like you said that, well, it wasn't called that, but that's how we refer to it now, in that it wasn't...
Well, it was naive and not naive because some of his proofs were very ingenious.
Right, but it wasn't axiomatized the way that current set theory is.
Well, they started to axiomatize it in 1904 or 1904.
And was that because of Russell's paradox?
This was part of it was because of Russell's paradox.
But maybe we should talk about that very briefly.
No, we don't want to talk about that because this would...
But I think
But what I want to tell you is that many mathematicians, there was a very strong resistance to this because they saw him as bringing in very doubtful notions into mathematics. The whole
Cantor.
Cantor.
Yeah, didn't was it Leopold Kronecker?
Yes.
Who ended up driving him basically into an insane asylum where he died?
No, that is completely... Look, if you read Bell's... Bell has a famous book, George Bell, called Men of Mathematics.
Men of Mathematics?
Yes, Men of Mathematics. Give a biographical sketch for lots of... He was very knowledgeable. He was a mathematician himself, but he had a very kind of conservative view about mathematics and a very limited view of mathematics. So he brought the whole thing about Kantor and Kronecker. When Jews fight one another, they fight one another to the death and things like that, which is nonsense. First of all, Kantor cannot be considered a Jew. Kantor was a mixture of many races, and according to Jewish tradition, perhaps he was 1/8 or 1/16. I don't know. In Nazi Germany, he might be considered a Jew, but it would be a borderline case. So first of all, and the Jews were proud to consider Kantor. Of course, they liked the idea very much, but he really wasn't. He was a borderline case. It wasn't a Jew.
Because there's scale.
Kronecker was a Jew. Kronecker was obviously a Jew. And Kronecker thought that Cantor brings in all kinds of very doubtful notions. He philosophizes. And
Didn't he say God made the integers, man made everything else?
Yes. Kronecker said, look, the integers are really, there is a mystery. Kronecker was a terrific mathematician. That is first to notice it. He was really great mathematician. Second, he was a very, very clever man because he decided that he'll go into the family business, and they were investors, and in industry and so on. So he took upon himself part of the family business and made it really flourishing business, so that he would be independent of what he wants to do later of any academic position. That means he could live freely on what he built up as a business. It was his building of a business, and then he said, okay, now I can do mathematics. And he did mathematics as a hobby, but did really, and they offered him a professorship in Berlin and Göttingen, and he gave it up. He didn't want a professorship, he wanted to be completely free. I think eventually he did get a professorship, and so, but Kronecker was one of the great figures of mathematics at that time.
I'm looking up Gothenburg.
Göttingen.
Gothenburg is in Sweden, so it's a completely different university, and I was totally wrong.
Yes.
But they sound somewhat similar.
Yes. So I think eventually he got a position in Berlin. Hilbert wanted him. I mean, Cantor had to work very hard to get a decent... Halle was a good position, and he was very much taken care of in Halle. Now, the truth about Cantor is...
We're in the middle of New York City. That's what all these sirens are.
Yeah, I know.
But
yeah, okay, fine. You can. That's okay. I like it.
I like it a little too. My dog doesn't.
No, I don't like the sirens, but I like it the fact that when you record something, it comes with the sirens.
Okay.
Because it gives you a sense of reality. No, I don't like the sirens, but I got accustomed to that. So this is New York. In any case, the more accurate story of Cantor was, of course, it wasn't that he was there was a personal fight between. I mean, Kronecker had very good reasons for his doubt, for his philosophical position, and he didn't have any particular hatred to Cantor and so on. It wasn't personal. And Cantor himself was treated very nicely at the University of Halle, where he was. And he was for instance, Cantor founded the German Mathematical Society. So he was a well-known mathematician. The fact that he couldn't get the position in Berlin or in Göttingen doesn't show that he was not an extremely influential mathematician. Hilbert thought a lot of him.
Can we return, though, to the mathematics side of things?
Wait a minute. I just wanted to... Cantor was a bipolar. He from time to time had depressions and he had to get vacations. And Halle was so much interested in keeping him that they gave him paid vacations. They gave him a free hand. He later on founded the German Mathematical Society. So Cantor was quite a successful mathematician.
Right.
In contrast to what you get, that Cantor went crazy because he tried to prove the continuum hypothesis and so on and so forth. This is not true.
Okay.
This is not true. Hilbert himself was very much... Actually, Russell's paradox was discovered before Russell by the people who was working with Hilbert in set theory. They knew about it, and they realized that the theory will have to be limited.
But you didn't want to talk about that. You wanted to talk about, are we moving straight from this now that we've discussed diagonalization to Richard's paradox?
That is correct.
Okay, so let's talk about that.
Okay, so Richard was a secondary school teacher in France. And he was a good mathematician, but he was interested in philosophy, and he was a very smart guy. And he gave a diagonalization paradox, which obviously showed that something, what was really a paradox, is not that this shows that the power set is bigger. And one way of getting what he did was to rephrase it. Okay.
So we're rephrasing the the string of zeros and ones, A1, A2,
no,
A3.
we rephrase the original argument of Richard,
Okay.
which was published in French.
Oh, well, then certainly rephrase that.
In one of the publications there. And the publication, I'll show you what was the paradox, but not in the way Richard did it about the real numbers, but essentially what he did.
Sure.
He used a semantic of natural language, French. And he says, look, every language, every human language is based on a countable set of symbols, actually an alphabet.
So for English, A, B, C, D, E, F, G.
Something like that, with punctuation marks and so on, whatever it is.
It reminds me of Borges's library already.
Yes. So, okay, so you can do it. And then you can also say that the English expressions, all the English expressions, what you can, sentences and so on, can be also enumerated in a sequence. It's not very difficult to see. You have a finite number of symbols, and then you take all the finite sequences of these symbols. This is also countable.
Okay. So, and when you say again it's countable, you mean there's bijective function with the natural numbers. Okay.
Yes.
In the same way that there was between the natural numbers and the even numbers.
Yeah, something like that. But finite sequences, if you have a set which is countable, the set of all finite sequences of members of this set is also countable. Okay?
Yeah.
One intuitive way of doing it, I don't want to, it's standard technique to enumerate all the finite sequences of a finite set, or even of a countable set.
Okay.
So he said, okay, so let us take so the set of all definitions of a subset. Okay, let's take all the definition of sets of natural numbers in English.
Okay.
In English. So there are countably many definitions of sets of natural numbers in English. Okay, they are countable. Okay, so let us use diagonalization and create a set which is not in this sequence by diagonalization. So you take the first and you switch the first and then so on.
So we've enumerated all the expressions?
Yes.
Okay.
You have enumerated all the English definitions of sets of natural numbers.
So it's essentially, instead of with symbols, it's 0, 1, 0, 1, 0, 1.
Something like that, but you can do the same thing directly in many ways. It's the kind of diagonalization.
Okay.
And so, I mean, in this case it would be French, but let's know we're doing it in English. So I describe to you an enumeration of all the subsets of the natural numbers, which are definable in English.
Okay.
Because the English definition is himself is a countable set. So I diagonalize it. That means I switch the first and then so on. And this also gives me a set of natural numbers. But this set of natural numbers cannot be defined in English, because I took all the definitions of sets in English and enumerated them, and this cannot be defined in English.
Right.
But I just defined it to you.
Because by assumption, we could list every number. That was the assumption. But then we've just shown one that's not on the list.
Yes.
So on the one hand, we've generated a number that's not on the list that is supposedly undefinable. Yes. But then, on the other hand, we've just defined it in English by explaining
by this conversation.
Right.
Okay. That's a paradox. And this is a paradox which uses a semantic argument, because it uses definition in English.
Right.
And this is really a contradiction.
Mm-hmm.
And the point of the contradiction is that you get the same paradox like the liar paradox, which you say, what I'm saying now is not true. So if what I'm saying now is true, then it is not true. And if it is not true, it is true, because that's what I'm saying now. So this is a semantic paradox. It is well known that if you have the semantic predicates or being true or false in the language itself and applying to the same language, you get a paradox. Okay? And this is because truth and falsity cannot be included in the language itself, so that you cannot get in the language itself a semantic characterization of its sentence.
And this is the importance then of sort of a meta language or a meta semantics or
Yes.
or meta mathematics, in which we are able to talk about the
The
language that
language,
we're using.
to talk, we invoking the truth, the concept of truth.
Mm-hmm.
The point is that you cannot do it if you want to do the semantics of the language, or to do something which is related to the semantics of the language. Okay? And this is known. This gives you the liar paradox. The liar paradox is essentially the same. You get a sentence that says about itself that it is not true. Here you get also a sentence which says about itself that it is not true. This is what Richard paradox gives you. Okay? So this is, and there is you can see exactly how it does it. When Gödel saw it, he said, yes, of course, when we know true and falsity, you cannot. But suppose instead of truth and falsity, I don't have semantic predicates, but I have only syntactic predicates. What is a formula? And also the notion of proof can be given in a way that it will be completely a formal syntactic argument. A proof is simply a finite sequence of formulas such that for every formula either it's an axiom and so on. You can give a complete syntactic description of the language inside the language itself.
Okay, before we get into Gödel, though, did Richard have any suggestions for how to resolve this
Yes, it does. It did.
paradox?
And this is what, first of all, Richard himself had a kind of a vague notion what is wrong there. And what is wrong there is that you assume that all of your definitions are listed, but then you define something which is in terms of the whole list of definition, and you think that there is a definition already there. So he said that this fact that you define an entity by appealing to a whole list of defined entities, and this entity itself is supposed to be already enumerated, this is wrong.
So there's an illicit move.
Yes,
Okay.
Illicit move. And Poincaré agrees with it.
It's sort of like moving a pawn 3 at the outset or something. It's just not something you're allowed to do.
Yes, I mean, you cannot, it's like that. The idea is very clear. Suppose, I'll give you an example. Suppose you have a group of people in the room, and you say the tallest person in the room. So assume that the persons are all of them different heights. Doesn't matter. You can make it a little bit more complicated and give up of this the assumption. But the tallest person in the room. Suppose that you can measure height to such an extent that there would be no two persons of the same height. In that case, the tallest person in the room makes sense. Now, this seems to us okay, because the notion of a person does not depend on these sort of definitions. Suppose George is the tallest person in the room. So he is a particular person, and you can define him as a person who was born to these people at that place, and so on. This is what gives it its existence. But if you can not define something in this way, in a direct, independent way, but you can only define something by appealing to the totality of object to which it is already belonging, this shouldn't be the case.
Well, that's the problem with Russell's paradox, right?
Yes, this is called predicativity.
Right.
So this should be the predicativity principle, and Poincaré gave it this name, the predicativity principle, that you cannot define something by appealing to a collections of objects to which this already exists and to which this belongs.
And in the case of set theory, that people were doing that with unrestricted comprehension,
right?
And that's what resulted in Russell's paradox. And
That
I think
is
right now it would be fine to just very briefly say what Russell's paradox is.
Well, you said the Russell's paradox is when you define it, the sets, then some there are members of the sets, okay, and then I don't that. There is a technical notion. Let's take the set of all sets which are not members of themselves.
Right.
And now you want to find out whether this set is a member of itself or not.
Mm-hmm.
So if it is a member of itself, since all the members are, since it is a member of this set, then it is not a member, and if it is not a member, it is a member.
Right.
Okay, this is Russell's paradox. This violates the predicativity notions, because you define the set by appealing to some totality of things to which it is already belongs, and this shows that this is not
right.
Okay, so this is a predicativity notion. Russell agreed with Poincaré that this is wrong, and his theory, the Principia, should avoid the the non-predicativity, should adopt the predicativity notion. This is Russell's position. Now, it turned out that you cannot do mathematics by having a predicativity-based position. There is no way of doing it. There are ways of doing. That means, suppose you have just sets and members of sets and subsets and set theoretical notions, and you want to define what the natural numbers are. So you must characterize them as a certain set with certain properties and so on. The natural numbers cannot be defined unless you violate the predicativity principle. Okay? So you cannot define the natural numbers, and Russell was aware of it. So in the Principia, he added one axiom, which is the reducibility axioms, which essentially it gives up on predicativity. What it says is, if it can be defined with according to that any definition which can be defined, and in this way there is also another definition which doesn't violate. It is really essentially it amounts to giving up the predicativity. It is not directly, but it's called the reducibility, that whatever I can do in this way, I can do in this way. The intuition underlying this really violates the whole point of the predicativity. And Russell says, yes, but we want to show how all of mathematics can be done in such and such a calculus, and so far we need it, so let's add this, and later on we'll take care of this.
Mm-hmm.
That was Russell's way of waving it. And then there was a famous paper which he published, which has shown presumably how you can do it with the predicativity notion, and the paper is gibberish.
Appendix B.
Appendix B.
Yeah, well, we talked about that already.
Yes.
So any last words on Richard's paradox, though?
Yes. Gödel realized that if you have syntactic notions, and among syntactic notions, the very notion of proof, in whatever it is, proofs are simply finite sequences which satisfy certain things and so on. So proof itself is a syntactic notion.
Right.
And you can do, and if the
proof in formal mathematics is just a sequence of
yes,
and inference rules. And
yes, you have a modus ponens, like a proof in first order logic, and you have the axioms itself. It's like doing the grammar of English in English. You can do it. If somebody knows English, you can teach him the grammar of English in English, and it makes sense. So Russell, no, what am I?
Gödel
realized that the whole thing can be done with respect to syntactic notions. And syntactic notion is also proof, provable, not provable, and so on. Or this is a proof, this is provable, and so on. And he said, if the language is sufficiently rich, I can do the whole syntax in the language, and then I will follow the reasoning of Richard's paradox. And instead of getting a sentence which said about itself that it is not true, which we know is contradictory, we will get another sentence which says about itself that it is unprovable. And this will give me interesting results.
Right, but that's a different story.
But this is the way Gödel came to the idea of the proof of his first independence proof.
Yeah, his first incompleteness proof.
Incompleteness.
And that's one of the most groundbreaking results in history.
Yes, and Gödel himself didn't understand exactly what he was doing there.
Well, let's save Gödel for another time.
Okay.
So
Gödel followed this, and you can see that the sentence that he constructs exactly mimics the way Richard paradox. And this also gives you the proof of what is called that for given any property that is expressed in the language, you can construct something which says about itself, I do not have this property. Mm-hmm. Which wasn't Gödel, but this was Carnap generalization of it and so on. So this Richard paradox was a gate which opened for Gödel all the enormous scope of constructing sentences that assert about themselves that they have or do not have a certain property.
Is the final word, though, on Richard's paradox, as far as you're concerned, just that we make that illicit move with impredicativity?
Yes.
Okay.
Yes.
Very good, then.
That is true. That is when you... Yeah, essentially that's what it is, but he didn't express himself in this way. Poincaré saw the general principle, Russell agrees with it, and that is the story.
All right. Great. Another one in the books then.
Okay, very well.
Thank you, Professor.
Okay, you are welcome.